Okay, in this talk, I'd like to discuss ongoing research into climate change impacts on maritime archaeology in the Middle East and North Africa, or MENA region. This is being done as part of the Maritime Endangered Archaeology Project, or MarEA for short. Just to give you some background on the MarEA project, since you may not be familiar with it, our aim at MarEA is to document and assess threats to the maritime, i.e. coastal and underwater archaeology, with an emphasis on the Middle East and North Africa. We've been running for about 2.5 years now, and we're based out of the universities of Southampton and Ulster in the UK. We work closely with the Endangered Archaeology of the Middle East and North Africa project, EMENA, which is based at Oxford, Leicester and Durham. And we try to work closely with partners within the MENA region as well, including academics, government bodies, and various consultants and so on. So within MENA, there are many threats to coastal and maritime archaeology. I'm highlighting quite a large selection here just to emphasize that MarEA is a comprehensive threat assessment program. We try to look at all possible threats. So for example, in MENA, one of the many threats has been rapid expansion of coastal settlements over the last 50 years. We can see nice examples here from Bahrain and Egypt. But in this talk, I'm going to focus very much on the climate change aspect of threats and disturbances. Given the audience, I'm sure I don't need to explain that erosion and flooding are two of the key threats we face, both of which can potentially accelerate in response to sea level rise over the 21st century. And the MENA region, like the rest of the world, will not be immune to this. There are two images here from archaeological sites in Libya, Tokra and Apollonia, which show the current impact of coastal erosion. I've also flagged up urban expansion or coastal development as a potential threat, but it's more of an open question at the moment as to how humans will respond to sea level change. Will they build more coastal defenses and so on? Or will there be increased migration to the coast as a result of climate change impacts further inland? We don't know at present, so that's an open question and one for the future. For now, I'll focus on coastal erosion and flooding as the key impacts we'll be exploring. So at MarEA, how are we researching climate change impacts and threats? There are three key ways we're doing this. Firstly, documentation. Secondly, integration of our data with external climate change or environmental models. And finally, shoreline change assessment using remote sensing and GIS. So in the rest of the talk, I'll focus on each of these in turn. And these images just show you some examples of shoreline change and how we try to measure it from Syria and Algeria. Okay, so the first of these is documentation. Documentation is at the core of the MarEA and EMENA approaches. Effectively, what we're doing is we're building a big database covering the MENA region, which provides threat and condition and disturbance assessments for each site. And by every site, I mean all known sites and unrecorded ones too. We effectively try to find sites as well as documenting known ones. To do this, we assess all available data sources. Generally, this includes literature published or grey, satellite and aerial imagery, historic, recent, anything we can get our hands on, basically. We record all the information using controlled vocabularies and certainty values. This helps us maintain consistency across the entire region and also enables comparability. And ultimately, all data is uploaded to the open access EMENA database, which is hosted by Oxford University. And by the time you see this recording, a relaunched version of the database should have been up and running for about a month now. On the bottom, you can see here our coverage. This was as of July last year, so coverage has increased since then, but you can see our core areas in the Mediterranean, the Gulf and the Red Sea where we've been documenting. Okay, you can see here an example of documentation. This is a site of Tokra in eastern Libya. It's a Hellenistic to Roman period coastal settlement which is threatened by coastal retreat. Published literature records 20 meters of coastal retreat in the 40 years up to 2004. And our own analysis of satellite imagery shows a further 11 meters of retreat from 2002 to 2019. Our partners in the region confirm that erosion is ongoing and unrecorded structures are at risk within this eroding cliff. And you can see this here on the satellite imagery on the left. The red and the blue lines respectively show the shorelines from 2002 and 2019. So you can see the difference between them. You can also see that most of the map surface remains are away from the coast, so any material in the cliff is obviously unrecorded. At the bottom, these are examples of the disturbance and threat assessments we've done for this site. And you can see they're broken up into different types of evidence or different types of category. Firstly, general category. Secondly, a specific type of disturbance or threat. And finally, a certainty value. So here we can identify a natural process of erosion and retreat, and we have definite certainty that has happened in the past and probable certainty that it will continue into the future. This means you could theoretically search the database for all sites which have been disturbed by coastal erosion and retreat, for example. Okay, moving on. Now we have all this information in the database. We can start to do some analysis of patterns that we can see. So this uses a subset of about 1,400 sites, as of which were recorded as of July 2020. And you can see from this subset that actually relatively few sites are impacted or threatened by erosion and flooding. So coastal erosion is here on these graphs, flooding is here. Less than 5% of our subset is actually affected, based on our results to date from documentation. However, the reason for this low value may lie more with limitations with our input data. If we're looking at undocumented sites, there will obviously be no previous documentation of any impacts. And if we use things like Google Earth imagery, there are slight offsets in georeferencing between different images, and also variations in temporal resolution, so how many images there are for any given site. And these make it harder to pick out more subtle or smaller changes in shoreline change. You can see the big changes, but picking out the smaller, more subtle ones is more difficult. So many of our sites are actually classified under generic water action or water and/or wind action categories, and we can see quite a high number here. And these effectively indicate that based on the site's location, it is very close to being to the sea, and thus will likely be impacted by marine processes or has been in the past, but we cannot say for certain which ones those are. Because of some of these limitations with our existing data, we've tried to explore other avenues to try and look at climate change impacts. We've tried to integrate our data using other models of climate and environmental change. And this just shows some examples of these previously published models. We have global surface water on the left, AquaMonitor on the right, and ListCoast, a large-scale integrated sea level and coastal assessment tool. And some of these focus on past change, which equates to disturbances in our terminology. Some of these focus on future change, which equates to threats in our terminology. And I'll show you some preliminary results from the analysis, again, based on a coastal subset of around 1,400 documented sites. So if we look at global surface water, or GSW, for those of you who don't know about GSW, it's based on 35 years of Landsat satellite imagery, and you can classify it in terms of land loss, which equates to coastal retreat, or land gain, which equates to coastal advance. So we can see here from our results that more sites are impacted by land loss than land gain over the past 35 years. So theoretically, or on the basis of this data, 12% of our sites have been affected by land loss or coastal retreat, and only 2% by land gain. So this fits in with our idea that some of the data limitations with our documentation are missing out some of the impacts of coastal retreat. But on the other hand, the number is not, 12% is not spectacularly higher than what we're seeing in terms of documentation alone. We can also try to look at flooding as well. We've done this by comparing site elevations from the coastal DEM-19 model with projections of sea level rise from the ListCoast project. And these include long-term sea level rise, or SLR, and extreme sea level, ESL, or basically storm surges. We've modeled these for 2050 and 2100 and included the IPCC's RCP 4.5 and 8.5, which are respectively medium and high greenhouse gas concentration pathways. So we can see from the numbers here, based on this modeling, 13 to 14% of sites will be coastal sites will be affected by long-term sea level rise by 2050, increasing to 25% if we take into account storm surges as well. And obviously, these values all increase by 2100 because sea level will keep rising. One thing you can notice is a wider range in these estimates, and this stems from the fact that the lower range is from RCP 4.5 and the upper range is from RCP 8.5. And this reflects the fact that there will be a post-2050 acceleration of sea level rise after, if you have a high greenhouse gas concentration scenario. So under RCP 5, sea level will accelerate, and this will affect more archaeological sites. The final thing we're taking out of ListCoast is its shoreline projections of shoreline movement, so shoreline advance or shoreline retreat. Again, we've modeled this for 2050, 2100, and RCP 4.5 and 8.5. These numbers are somewhat more alarming than the previous ones. Based on these estimates, up to 33% of sites may be affected by coastal retreat by 2050, increasing to 43% by 2100, with impacts across the region. There is a caveat though, and it is quite a big one. The original ListCoast model has been criticized by some coastal scientists as being overly alarmist and an oversimplification of reality. It kind of has to be in order to be able to work on a global scale. So it doesn't take into account things like human action, such as shoreline protection, or the local to regional scales complexities of shoreline change. So we are using it, but we're kind of viewing it very much as a worst case scenario projection. So what we have with these data is we've got a sense of how big a problem climate change may be in the future, and also we're starting to get hints of where some hotspots of impact are. Based on the results I've shown you, a lot of those hotspots were kind of controlled as to by locations where we've done the documentation to date. But as we're proceeding further and further, this will be smoothed out and we'll actually start to see genuine hotspots of impact. But what we're trying to do now is look in a little bit more detail at certain key sites and locations. And the reason for this is twofold. One, we want to see how well these broad scale models actually work on a site scale. And secondly, the actual management of these sites will happen at national and subnational levels, not these kind of big regional scales. So we need to have in-depth knowledge at the appropriate scale for heritage managers. This is what we're doing here. So I'm going to give you an example here, again from Eastern Libya, using the site of Apollonia, which is a Hellenistic, Roman and Byzantine harbor. There's numerous ruins and remains all over the site, underwater, on the coast and on land as well. And on the right-hand side, you can see outputs from two models, two shoreline change models. So this is Aqua Monitor at the top, global surface water at the bottom. For Aqua Monitor or Shoreline Monitor, these red transects indicate where there has historically been erosion, and white indicates where there has been historically stability. Based on this, you'd see the core historic site delineated by this yellow dashed line, according to this model, actually appears to be okay. All the erosion concentrates to the west. But global surface water, on the other hand, also picks up that erosion to the west, but suggests there are also hints of erosion here in the center part of the site where I'm indicating. So we thought we'd explore this further using higher resolution imagery, and we've used a combination of aerial imagery from 1949, declassified spy satellite imagery from the 1970s, and a range of more recent satellite images. And what we've tried to do here is we've tried to trace the eroding edge so we can work out how fast it's been changing over time. And you can see the kind of eroding coastal edge showing up quite nicely all across this particular image. And these are our results, as you can see here. So the top image shows the shoreline change rates for 1949 to 2010, and the bottom shows the last 10 years, 2010 to 2019. Each of these transects is color-coded to show the rate of change. So warm colors indicate coastal retreat, blue colors indicate stability or advance. So historically, you can see this part of a site, despite this eroding edge, has been relatively stable. Erosion is concentrated here on this side of this incipient tombolo, a little bit here on its other side, and this side too has been relatively stable. Fast forward to 2010, and our data suggests an increase in erosion rates. They're still quite slow, less than ½ meter a year, again with the fastest rate of erosion concentrated here. But there seems to be a transition of stability, transition to stability on this side of the tombolo. This area though has again seen fast retreat. So we think from this that we're starting to see an acceleration of erosion across these bits of the site for sure. So what does this actually mean for the future? We can try to project these rates forward in time to look at likely effects. And these are shown by the yellow lines here. So dashed for 2050, solid for 2100. So this is basically where the coastal edge would be in the future if it was moving backwards at the rates we see over the last 10 years. However, we also have to consider that erosion rates may increase over the 21st century in response to accelerated sea level rise. So we've used list coast to give us the sort of the worst case scenario. So this is list coast 8.5 for 2050, dotted red line, solid red line for 2100. And you can see it goes much further inland because it's the worst case scenario. If we start to project these into individual structures, you can start to see the effects of what might happen. So these are sites located directly on the coast, which are currently threatened. So you can see here by 2050, this site will be double that based on present rates, but it will lose a chunk, probably about, maybe a third of its surface area under a worst case scenario. Similarly for 2050 or for 2100, you could be seeing a difference between, say, 25% of the site versus 50% of the site being lost under a worst case scenario. And you see the same effect for here. We can probably confidently say that this Byzantine structure over here will pretty much be half gone by the end of the century. as will the seawardmost parts of the Roman baths here. And under a worst case scenario, you may be looking at the Western Church, the central church being threatened, as well as half of the Roman baths being gone. We also have to remember that every time the shoreline retreats, unrecorded material may be exposed, such as here on this part of the foreshore, and will also become immediately at risk as it's directly exposed to waves. So to draw this to a close, hopefully I've given you a sense of what we're trying to do with MarEA. We're trying to produce a comprehensive threat assessment currently focused on the Middle East and North Africa, which includes the consideration of climate change impacts. Our key tool is our database, and we can use this directly using the documentation results, or we can try and integrate the database with external models of climate and environmental change. And hopefully this will form the baseline data, which is currently lacking for large parts of the Middle East and North Africa. So we can start to see some of the general patterns which are emerging from this, which suggest that many, but not all sites will be at risk over the 21st century. How you want to interpret those numbers kind of does depend whether you're a glass half full or a glass half empty person. We've also tried to develop more detailed shoreline change assessments, which can highlight complexities which go at a site level, and which can directly feed into future management plans. And this links to my final point, because ultimately there's no point in doing this if we aren't actually supporting our local partners on the ground, because ultimately it's they will be the ones who have to manage this heritage and respond to this problem directly. So for example, we've been supporting our Libyan colleagues in particular, who've been doing some excellent survey work of these threatened coastal sites. We've been supporting them through training, documentation and remote sensing work, and they've been doing an excellent job, and we hope to extend this kind of approach to other regions in the future. Okay, to wrap up, I'd just like to say thanks to our funders for supporting us, and also thanks to various colleagues as well whose support has been invaluable to this project.